Cool. So question 1, we're told that there are 20 people who are known to have a disease. And so we also know that the probability a patient recovers independent of each patient, and this is the same for each patient, is 0.8. So fixed number of people, fixed probability of success, binary outcomes, independent outcomes. That to me says binomial distribution. So let's first define our random variable. So we know that we're going to let y be the number of patients that recover. All right. Now, given that, we know the distribution for y straight away because we've discussed it's binomial. So we know that y is distributed binomially with 20 trials and 0.8 probability of success, right? So 20 people, 0.8 probability of recovery or success. Okay, so that's the setup. So now let's go ahead and calculate the first probability. Well, answer the first question. So A says, what's the probability that exactly 14 people recover? So you want to know, what's the probability that y equals 14, right? That the random variable does indeed equal 14 in this case. What's that probability? Well, we're going to use the definition of the binomial distribution and say that the probability is given by 20 choose 14, which is the number of trials choose the number of successes, multiplied by the probability of success raised to the power of the number of successes, multiplied by 1 minus the probability of success raised to the power of failures. Right. However, this 1 minus 0.8 can also be written as 0.2, which is the probability of failure. Up to you. And if you run that through calculator or R, you get 0.1091. Now, if you look at the written solutions, you can see how to do that. This bit here in R using the D binom, but I'm not going to write it here on the screen. Great. So that's part A. Now part B is much the same idea. We have our same random variable y, which is the number of patients that recover, but we now want to know what's the probability at least 10 recover. So at least means more than or equal to. So you want to find the probability that y is greater than or equal to 10. Now, we could calculate that straight out, but it's annoying. What we'll do instead is we will write that as 1 minus the probability that y is less than or equal to 9, right? Because if you're greater than or equal to 10, the complement is being less than or equal to 9. Now, the reason we do this is because this term here we can calculate straight into R using P binom, but once again, look at the solutions for how to do that. How are we going to calculate this by hand or with a calculator? We're going to look at this. So let's consider the probability that y is less than or equal to 9. Right? So this can be written as the sum from I equals 0 up to 9 of the probability that y equals I. Right? So now that's going to be the probability of y equals 0 plus probability equals 1 plus all the way up to equal to 9. And then we can expand that out to be the sum from I equals 0 up to 9 of 20 choose I, right? Because we want to see the probability that y equals I, times the probability of success, which is 0.8 raised to the power of I, times 0.2 raised to the power of 20 minus I, right? Because you have I recoveries, you must have 20 minus I non-recoveries. Yep. Now, if you put that into your calculator or put this bit here through R, what you get is a probability of 0.9994. So quite likely that at least 10 people are going to recover, which is really good. Great. So the next one, up here says, what's the probability at least 14 but less than 18 recover? Okay, so we have the probability that at least 14, so that is that y must be greater than or equal to 14, right? But we know it has to be less than 18. So less than 18. So we're going to be squeezed in between those two. Now, the first thing we're going to do, once again, is we don't like having this less than sign. We want to always have it in less than or equal to. So we'll write that as the probability 14 is less than or equal to y is less than or equal to 17. Right, so those two lines are equivalent. And now what we can do is we can solve this two ways, right? So the first way is to simply write out like we had earlier with our sum. So we have I equals 14 up to 17 of 20 choose I, 0.8 to the I times 0.2 to the 20 minus I. Right? That's perfectly valid, but the only way you can solve that is by hand. Whereas what we can also do is we can think of it as, take this line here and say that that is equal to the probability that y is less than or equal to 17 minus the probability that y is less than or equal to 13. Alright, because now this is the CDF and this is the CDF, and we can calculate both of them on R. And so if you do either of these methods, you will get a value of 0.7072. Great. Now, why does subtracting these two CDFs work? Well, let's get some colours out. So this one here is saying take it from 0 up to 17. Right? It's saying calculate that whole thing. But what we're doing then is we're subtracting, about there would be 13, right? We're subtracting off all of this, right? Including the 13. So all that's left is this area here, which would be 14 through 17 inclusive, right? So that's, if you have y greater than or equal to something and less than or equal to something, you can always subtract them using this idea. Cool. What's the last part? Last question says, what is the probability that at most 16 recover? Okay, so to do this, we're going to first write it out in our probability notation. So part D is, what's the probability that at least 16, sorry, at most 16, sorry, my bad. So at most 16 says that we can't have more than 16. We could have up to and including 16. So the probability that y is less than or equal to 16. My bad. So it says most, at most 16. Now, we can calculate this, once again, just as we do writing out the sum over I. So we need all of them from I equals 0 up to 16 inclusive to be successes. So that would be 20, choose I, times the probability of success to the number that succeed, probability of failure to the number that fail. Right? Now, if you evaluate this, you will get something like 0.5886. And once again, you can type this into R. I'll go through this one in R just because it's one of them and you can take this principle everywhere else. So this probability is equal to P binom, right? So that's calculates the CDF under a binomial distribution. Now, we want to find the CDF, the probability that y is less than or equal to this value, right? When there are 20 trials and a probability of success of 0.8. And if you type that into R, you will get the same thing but with more decimal points. So like 0.58855, ... so on. Hope that makes some sense, but more importantly, we understand the mathematical concepts. Cool.